Welcome to DWBIADDA channel. Please subscribe for latest training videos.
Hello, welcome to Pytorch tutorials. Today I'll give you a brief idea about different optimizer functions in Pytorch. These optimizer functions are necessary because when you are working on a project in Pytorch and building a deep neural network, you have to try different optimizers and different learning rates, and these are called hyperparameters. So you have to check different hyperparameters and decide which one works best on your system, on your dataset. And that's how you get the most out of your data. So understanding these hyperparameters is extremely important when you are working on a deep neural network project. So today I'll make this video about the optimizer functions that are available in Pytorch. So without further ado, let's import Torch, Torch Vision, Torch.nn, Torch Vision.transforms, Torch Vision.datasets, Torch.autograd, and time, just like the previous video, to check how much time each step is taking. You might remember in the last video, we worked on fashionableness dataset, and today we'll work again on the fashionableness dataset and show you how different optimizer function gives us different accuracy on the same dataset. We are keeping the batch size 100 just like the previous video, but the number of epochs has been changed to 20. The deep neural network model, or the MLP, is same, and the training and testing functions are also same. So let me run the function first so that it will run, and I'll discuss about the optimizers, because training the model takes a bit of time. So first optimizer is ADAM. ADAM stands for adaptive momentum. Momentum method is a very good method of optimizing. Basically, this optimizer functions decide how you update your weights and biases at each backpropagation stage. You might remember that when you do loss.backward, you take the backpropagation of the loss, basically the derivatives. And in optimizer.state, you update your weights and biases to run on the next epoch so that you can reach the minima of the loss function. And if you reach the minimum of the loss function, it means you have optimized your system and it's giving very good accuracy. So that's our goal, to reach the minima of the loss function. So the first optimizer is ADAM. Here we are passing the learning rate. Here I have not mentioned learning rate. The default is 0.01. I have kept two betas though. It says 0.9 and 0.999. Betas are necessary for running average calculation. You can read about it on Google about how adaptive momentum or momentum method uses betas to adjust the running average. There is a term called epsilon. Epsilon is added to the denominator. There is a function that we use apart from the learning rate in ADAM that comes in the denominator, and we try to reduce the denominator, but if we reduce it too much, we might run into a divided by zero error. To prevent that, we use an error term. We introduce an error term knowingly that is called epsilon. and we keep it very small so that we don't run into divided by zero error. Once we run our model with Adam, next optimizer is SGD, that is stochastic gradient descent. Stochastic gradient descent is a variant of the normal gradient descent. The difference is stochastic gradient descent takes one input value or input data at one time, and it calculates the loss on it. And you can understand from that it's a very slow method, stochastic gradient descent. And the word stochastic means it's the training process is random. What we have to do is to run on stochastic gradient descent. We will load our data again and we'll define our training and testing steps, and we will run our stochastic gradient descent. Right. In stochastic gradient descent, we are using the model parameters and we are taking the learning rate. The learning rate has been set to 0.001. One thing here is, if you keep the learning rate small, your model will learn slowly, but the learning will be better. But if you keep it too small, it will take too much time to train your model. Again, if your learning rate is high, let's say 1 or 2, for example, your model will learn faster and it will take lesser time, but at the same time, you will learn less parameters from your data. So there is always a trade-off between the speed and learning of your model. The last thing is Rmsprop. Since SGD is taking its time, I'll discuss about the Rmsprop in the meanwhile. Rmsprop is another optimizer in Pytorch that you can use. You can read about Rmsprop in the documentation of Pytorch. I'll just tell you about the parameters it has, because understanding these optimizers requires some understanding of mathematics. Since it is out of our scope, I'll just discuss the parameters. So in Rmsprop, obviously you have model.parameters, you have learning rate. There is a term called alpha. Alpha is a smoothing parameter which is required for Rmsprop to run faster. And obviously there is a epsilon term, like I explained before, to prevent the model or the optimizer function from running into divided by zero error. The centered parameter helps you normalize your weights, adjusting the weights. You can try with centered equals to false, you can try with centered equals to true, and see which one works better on your system. The training method will take some time, and meanwhile I'll talk about some other optimizer functions that are available in Pytorch. Some other optimizers are ADDA, ADDA delta. These are very good optimizer functions, and they are different from each other with slight variance. Okay. Once our optimizer functions are used to train our model, I have taken the training losses, the test losses, and the test accuracies to check which one is working better on our fashion MNIST dataset so that we have an idea which one we should use in this scenario in our model. So when you are working on a deep learning problem, you have to play around with these parameters to check which one is working good for you, and you should take the best one. Okay, the training is done. Now we can see which one is working better on our system. You can see that for training losses, SGD does not perform as good as Rmsprop and Atom. Rmsprop and Atom are actually overlapped. You can see a small difference between them, although eventually they reach at the same place. For the test losses, again, Atom and Rmsprop outperform SGD. In fact, Atom and Rmsprop are working as good as each other, I would say. The last one is test accuracy. This is the most important part. And again, you can see that for test accuracy, Rmsprop and Atom has outperformed SGD. So SGD requires more number of epochs usually. That is from experience, I can tell you, because it's a slow process and the method is stochastic. So you can try using Atom and Rmsprop and see which one is working better on your system. Thanks for watching.